one by one. Okay, I've started recording this for people who might not be able to make it, and I'll start sharing my screen. Thank you for coming, everyone. This is a knowledge share on the Python core object model. So we're going to start at the very beginning with the sort of basics of classes and work into the inner life of Python objects, inheritance, and a little bit about multiple inheritance, why you shouldn't do it, and how it works, and why it's a bad idea, what it's good for, and so on. I've been teaching Python for over a decade. I really enjoyed doing it. I was on the Python core development team for a little while, looked after unit test in the standard library, and wrote unit test.mock, which is, and that sort of journey is where a lot of my knowledge comes from. And I'm going to start with, it's a little bit pretentious, but it's the bit I always start my training with. So Python, we can describe Python as an object-oriented, high-level, object-oriented, dynamically typed, interpreted, general-purpose programming language. And high-level means compared to lower-level system languages like C, and we can do a lot with a few commands. So I have a trick question for you. It is a trick question. If we're working in Python, which is quite a high-level language, what's the fundamental language of the machine? What language does the machine speak? And there are two wrong answers that I hope for.
Binary is the one I'd go for.
Yes, well done, Ashley. Yeah, that's one of the words. And the other one is machine code, which would be an equally valid wrong answer. Why is that a wrong answer? Particularly binary. That's what we tend to think of as the lowest level language of the machine. But binary, but Ed has raised his hand.
I reckon, is it the instruction set for the architecture that it's running on?
Well, that's good. That's, I suppose you would call machine code. Machine code is the instruction set, and it's a perfectly valid answer. But the thing is, the ones and zeros, if we look at an assembler, which gives us a representation of the instruction set, like JMP for jump and so on, this kind of stuff. Ones and zeros are a human abstraction. They're human concepts. It's a very low-level representation. The 0 corresponds to a low potential on a wire, doesn't it? And a 1, a high potential on a wire. But fundamentally, binary is still a human construct. It's an abstraction for humans to understand. The actual language of the machine is the electromagnetic dance across wires and etched silicon, choreographed by the beating of the quartz crystal at the heart of the machine. It's the signal, that deterministic dance. The machine knows nothing about ones and zeros. They're human ideas, and it knows nothing in particular of objects. What's actually happening inside the machine, that signal, that electromagnetic dance, is vaguely related to our objects. But the purpose of objects, the purpose of things that we create with Python, they're for us. They're for a communication, a two-way communication from us to the machine and from us to other developers. They give us ideas to think about. Programming languages are frameworks that enable us to reason about the state of the system, to reason about the behavior of the system. They give us a way to visualize what we and think about what we create. So the programming language is fundamentally there for us. It's there for, this is why in Python, simplicity and clarity are the key virtues. If someone in Python says your code is clever, that is not a compliment. So we use the tools that the language gives us in order to create things we can think about, things we can communicate about. So when we're programming, we are attempting to solve real-world problems. So what we're creating corresponds to something in the real world. So if the way you think about your code cleanly maps to the way you think about the problem, if you use good abstractions in your code, then it's going to be easier to maintain and think about. So that's what objects do. They give us a way to build abstractions that enable us to think about things. My first professional programming gig was with a firm in London called Resolver Systems, and we were building a spreadsheet that was going to replace Excel for financial companies, and it didn't. But it was a great place to work. We did a lot of thinking about design, and the core design of the system, this spreadsheet, we had a workbook class. The workbook would own worksheets. Worksheets had cells, rows, and columns. There was a dependency analyzer and an execution engine. And because of this clear design, the way we thought about the spreadsheet mapped very, very cleanly to how we thought about the code. And when you came to write code, you knew exactly where it went. So that's one of the purposes of objects. They can provide structure. They provide ways of thinking. They can also wrap up algorithms, the strategy pattern, and so on. So we can use objects to build things. So let's look. I'm going to start at the beginning with classes and class definitions, and it's all going to be stuff you're familiar with. I hope you don't feel patronized, but we're going to move on to some more interesting stuff as we go. And I may not, if you're lucky, I may not take the whole hour. Okay, so pressing buttons, the Python object model. Python is an object-oriented language. My mantra when training is everything is an object. Every object has a type. You can only perform operations appropriate for the type, and it's the type that's responsible for creating new instances. And already we've got some object-oriented jargon there, haven't we? Types, instances, and so on. And so the big idea of object-oriented programming, it doesn't enable us to do anything that we couldn't do previously with procedural style programming. With procedural style programming, you have function data structures and then functions or procedures that operate on those data structures. The big idea of object-oriented programming really is we just bundle those together. And even if you don't create classes in Python, you're still in Python, everything is an object. So you're still using object-oriented programming. Some a very simple example. We have some data and it's a string. Its type is str. You have some more data, which is a different string. And it has the same type. So because we know the type, we know something about the behavior of the object. We know the methods it has and the operations it supports, like concatenation. They're not equal, they have different data, but there's a lot about them that they share in common. For example, both of them have an upper method. And so with methods, we use the dot operator, the attribute lookup operator, to look up the method, and then we call it. And if you want to think about, well, what is a method? A method is a function that operates on an object. So you can kind of think of it as a function that takes some data. And where does it live? Well, it lives on the type. Everything that lives on the type is shared by all the instances. And in fact, if you think about methods like this in Python, you find that that's actually how Python works. That the methods are functions that take the object as the first arguments, and they live on the type. And everything that lives on the type is shared by all the instances. And obviously, with the class statement, we can create our own types. Type and class are synonyms in Python. If we look at the str type, it's even got the word class in it. We tend to use the word type for the built-in types. We tend to use the word class for user-defined classes, but they're synonyms. They mean the same thing. But because data and other, although they have different values, although they contain different data, because they have the same type, they have the same behavior. So one of the things I love about Python is that with a limited amount of knowledge, a certain amount of information, you can understand a lot about the Python world and the Python object model. And there's sort of a couple of places we really see that. And I guess I'll introduce that here. Everything is an object. As we'll see in a bit, inheritance establishes an is relationship. So when we say everything is an object, we mean that all classes inherit from objects. And so object is an instance of itself. So what are these types? If I create a class, everything is an object, every object has a type. What's the type of a class? Does anyone know the answer?
An object.
Well, it is an object, but it's a type. These are types. I said class and type were synonyms. We're creating types. And because every Python is a dynamically typed language, types are determined at runtime. And don't forget, everything is an object. Every object has a type. You can only perform operations appropriate for the type. And it's the type that's responsible for creating new instances. Who is an instance of type? Type is actually called at runtime to create types. And when we look at the class statement, I'll show you that in practice. So strut is a type. So what is the type of type? Well, type is a type. So these are the two places, well, two of the places where the Python object model folds back on itself. Object is an instance of object and type is a type. So the interpreter has to cheat to set this up. But it creates this sort of little world, this consistent little world within which we can know things. Things can definitely be true and we can use it. It creates a framework we can build things with. So type is an object is a type. Okay, I've probably succeeded in confusing you, which at least is something. So we've looked, I've just been showing you that we have objects that have data. String has data, its value, and they have method, these functions that are attached to them, these functions that operate on the data. And you're well used to that, even if you're not creating classes yourself. We can define custom classes. We can create our own classes with the class statement. And there are three important components to a class. One of them not shown here. That is the class name, the tuple of base classes that we're inheriting from. And if it's not specified, we inherit from object. And then there's the body of the class. And that's all of the code indented inside the class. Usually a bunch of functions, doesn't have to be a bunch just functions, and those functions become methods. So those are the three components that Python uses to create a class: the name, the tuple of base classes, and the body of the class. And type is called at runtime to create these. So we're used to using type to find out what the type of something is, but there's another three argument form. And this is actually useful in practice. You're probably used to factory functions, working with closures, functions that create functions. If you've ever used name tuple from the standard library, that's a function that creates types. It builds types at runtime, and that's something that's can be very useful to do. You can have a factory function that builds classes for you, builds type specialized on the input to the function. So the three components of a class. Let me write a function first. This is going to go into the body of the class. So there's a function. So now I can create a thing class by calling type with the name of the class, tuple of base classes. I could either, so where you have a tuple with just one member like this is the syntax, and I say that's not a tuple, it's a oneple. But no one ever thinks I'm funny. Okay. And the body of the class, which is a dictionary. Don't forget a function definition. What Python does when it executes this code is it creates the body, it creates the function object, but it's also an assignment in the namespace it happens in. After the function definition has been executed, the name here, dunder init, which is shorthand for double underscore init, double underscore, the name dunder init is bound to, refers to the function object. So when Python executes a class definition, it kind of creates this temporary namespace that this code is executed in. So the function objects, which become methods, they are executed. And then in that temporary namespace, it's actually a dictionary. The names of the functions are bound to those objects. And then that creates a dictionary, which is used to create the body of the class. So dunder init equals, and we can pass in the init function I've just created. And this is going to create a class, which is exactly the same as if I've written it using a normal class definition. What is it? Well, it's a type. I've just created a type. Everything is an object. Every object has a type. You can only perform operations appropriate for the type. And it's the type that's responsible for creating new instances. And that's customizable in Python. Classes that create classes are called metaclasses. So in Python, the type of a class is a class, and type is the default metaclass, but we can overwrite that and provide custom metaclasses. And you shouldn't do it, but it's still useful and interesting to understand the state of the world. So it's a normal class. I can instantiate it. This is going to call the initializer. Dunder init is not technically a constructor. Python has two-phase object construction. There's a dunder new, which we usually don't override. We inherit from object. Dunder new creates the instance, and dunder init is the initializer. It receives self. We'll look at that in a second, but the instance has already been created by the time we get to dunder init. So dunder init is the initializer. It initializes the instance, typically just setting a bunch of attributes. Don't do work in initializers. Do as little as possible. So there we go. My initializer was called and X was set. So that's type as a type factory for creating classes. And that's what actually happens. Type is the default metaclass. This is what happens at runtime when a class statement is executed. So those are the three components of a class: the name, the tuple of base classes, which will be just object if you don't specify anything explicitly, and the body of the class. If we look at these function definitions, these method definitions that make up the body of the class, we'll notice a couple of things. There's this funny double underscore method, the dunder method, the init, and I've already talked about that. That's the initializer. In other languages called a constructor, but it's not really a constructor in Python. And all of the methods, all of the functions take self as the first argument. In other languages, self is called this. It's just a convention to call it self. So if you really want to annoy Python programmers, call it this instead. Don't do that. So here, frobulator is the type. We call the type as if it was a function, and that creates an instance of the frobulator type. So when we call a method, when we look up a method, let me show you this with inspect. Inspect is one of the hidden gems of the Python standard library. A lot of useful introspection stuff there. And inspect.signature will tell us the signature of functions. It was originally written to support mock, a little bit of Python history. Here we go. There's only one method, dunder init. If I look it up off the class, treating the class as an object, it's just a normal function. And it's a function that takes one argument, takes self. If I look up the same method off the instance, I get back a function or a callable object that takes no parameters. If I look up the method off the instance, instead of getting a function, this is the original function I created. In fact, I'm pretty sure if I do thing.dunderInit is init, I'm pretty sure that's going to say it's exactly the same object. T.dunderInit is very definitely not the same object as thing.dunderInit. What's happened when we look the method off the instance, Python creates a bound method for us that has self already bound in. This is an example of partial application for those of you who know anything about functional programming. The first parameter self has been partially applied to the function. And you can see it's if you look at the last few figures of the ID there. If I look at thing itself, T itself, FD4890, it's the same. That is the self. That's the instance is the self that has been bound in. And this is what enables us to write methods, write them once, and have them to be shared and used by many different instances. So that, I'm sure, is straightforward, and you're used to this. You write classes, that you write functions inside the body of the class. Those become methods, and it's the instance when we call the method from an instance. The instance is passed in for us as the first argument. What you may not know is that how that happens is by something called the descriptor protocol. If we look at the init, and it's the same protocol. These double underscore methods, they're called magic methods or special methods or protocol methods. Python has a bunch of protocols, and the object creation protocol is one of them. And there's two methods involved in the object creation protocol, done to init and done to new. Hopefully we'll have time that we can look at the string representation protocol and look at the two methods of those. In other languages, it's called operator overloading. We can customize the behavior of the objects by implementing these protocol methods. And the descriptor protocol is a protocol that's involved in attribute lookup. When you do t.x, we're looking up the x attribute on the object t. This is the dot operator, the attribute lookup operator. And there's a protocol as to how that happens, and it's customizable. The default one is object.get attribute. You can override that and completely customize attribute lookup. There's also getAttra, which is ever so slightly different. Won't go into the details now. And the descriptor protocol is part of what done to get attribute does. And it's the same mechanism by which class methods and properties and static methods and instance methods all work. There's a consistent set of rules. And actually functions have a done to get method. And when you look up an instance, when you look up a method on an instance, Python finds it on the class and it passes in the instance and the class to done to get, and it actually calls that and returns whatever that returns, and that returns a bound method. That's the descriptor protocol. That's to understand the details of that is pretty advanced. You can write custom descriptors. It's something I've done once professionally, not something that comes up very often, like meta classes. Okay, so that is a class definition. And the methods, the initializer done to init, part of the object creation protocol. It's called every time you instantiate an object. We instantiate objects by calling the class. And when we call methods from an instance, Python passes self in for us. It passes the instance in for us. And because we can pass in arguments into the instantiation call, every instance can have different data. Instance data is typically stored as attributes on the instance, on the object. So here we have the objects with different data, but the same set of methods, the same set of behavior. This is the initializer. If anyone does want these slides afterwards, feel free to message me and I'll be happy to send them. So there are three fundamental operations we can do with attributes: attribute fetching, attribute setting, and attribute deletion. And by default, Python objects are open. You can create and modify any attribute on an object, which is a double-edged sword. With great freedom comes the ability to create great mess-ups. Attribute deletion is pretty rare. In general, you want your objects to always have the same shape, always have the same set of attributes available. So in general, you want to initialize all of your attributes in the initializer, and you want them to have the same set of attributes. There are some use cases for attribute deletion. And there are some built-in functions that correspond to those operations. And with getAttra, we can supply a default, which is nice, the 3-argument form. Bound methods I've already talked about. Everything that lives on the class is shared by all of the instances. So anything we define in the class is then available on all of the instances. And they don't have to be methods. We can have class level attributes. So if I create another instance of thing and I attach to the thing class some attribute, I can now access that from all the instances. Everything that lives on the class is shared by all the instances. So you can have class level attributes, so class level configuration, class level caches, that kind of stuff. If you have classes that hold a lot of data, but much of it is the default value, you, instead of setting on every instance all the default values in the initializer, you can set them on the class, and then individual instances only need to override the ones they're changing. But there's this fundamental difference between an instance attribute and a class attribute. If I do t.attribute equals 99, I'm setting an instance attribute. T2 is still getting the default from the class. I can change the one on the class. T2 has changed, but the T has got an instance attribute that shadows the class attribute. I've just seen how much time I've already taken. Too much. I'm waffling, sorry. The interesting thing is, if I delete the attribute of T, I then restore back the access to the class one. So now, when I look up attribute on T, it will get the class one instead. So there's two places fundamentally that attributes can live, on the instance or on the class. So here's an example for class level configuration. Instance level attributes shadow the class level attributes. Or we can use class level attributes for customization. I'm going to skip ahead a bit. I'm going to skip properties, which I'm sure you're familiar with. Properties are another descriptor. Computed attributes. Fetching the attribute triggers the getter to run, and setting it triggers a setter to run. And we have for private members in Python, for private data, we have this convention of a single leading underscore. So in this example, self._shares equals values. That shares is the public API. That's guarded by the property, but the real data is stored in this private backing variable. And the fact that it's private is indicated by the single leading underscore, a community convention, not enforced by the language, but understood by everyone. If you mess with it, you get what you deserve. Under slots creates non-standard Python objects, so try to avoid using them. They're a memory optimization. Darius is raising his hand. Yes.
Yeah, I've got only a question that it could be connected to these attributes, like static methods. Yeah? Is similar mechanism for this, or there are different?
Which one? The private ones?
Yeah, not the private. In general, you show the example when you instantiate and assign value to the, not the instance, but
to the class. Are they the same as static? Yeah. I guess they're analogous. Sure. Yeah, it's kind of similar idea. I think it's a while since I did a bunch of C#, but it's been a while. Yeah, kind of analogous. Yeah.
Quick question: is that a typo on line 4?
Of which of this code?
Yeah, that page self_shares. Is that what that should be?
No. So the interesting thing is
up a little bit, where you're in your definite.
Yeah. So when the initializer is called, the instance has already been created and is already working. It just hasn't been initialized, and we can refactor going from simple attributes to properties, and it's fully backwards compatible. So in the initializer, it's very deliberate to leave using the public API, because now we get the type checking in the constructor, in the initializer. Self.shares equals shares here will trigger the setter. And so if you attempt to instantiate this class with, say, a string for number of shares, it will go through the property and it will raise an exception in the initializer. So it is a little bit funny. You would normally expect it to see instance attributes initialized directly in the initializer, but in this case, it's using switching from a simple attribute to a property. the syntax is exactly the same. It's fully backwards compatible. We don't need to change any code, including we don't need to change the initializer there. That works fine, and it means we get the type checking in the initializer there. Ed has a question.
So the initializer doesn't create the instance; it modifies the instance that's already been created.
Yeah.
How is that different from new?
New creates the instance.
Okay.
And we'll typically so if you implemented the singleton pattern, you might have done to new return the already created instance instead of creating a new one. If you have immutable objects that can't be changed after they've been created, you might need to do that in dunder new instead of dunder init. And typically, it's actually object.dunder new that does under the hood the memory allocation, creates the object, etc. So in dunder new, if you override it, there'll still be a call to super.dunder new, which will go up to object to actually do the creation. So dunder new creates and returns the instance. Dunder init receives the instance and is not allowed to return anything. Returning anything other than none from dunder init will actually raise an error.
Yeah. Okay. So if you want it to be a failable operation to initialize something, you would either need to change dunder new or use this getter setter pattern to intercept.
I mean, if you raise an exception in dunder init, then the object creation will fail. It will be allocated, the exception will be raised, it will be garbage collected.
Okay. All right. Thank you.
Cool. So inheritance, tool for code reuse, tool for specializing existing objects. And we have two sets of synonyms: the parent class, the superclass or the base class, and the child class, the subclass, and the derived type. And this is the syntax for inheritance in Python. Again, something I'm sure you're familiar with. Using inheritance, we can modify and extend the parent. And when we inherit from a class, the child class gets it inherits everything. It gets the full API of the parent class. So it's quite a broad tool, and a lot of people prefer composition over inheritance, because where you're inheriting, you get the whole API, and often that's what you intend. Here's a simple example of using inheritance to extend a parent. We inherit from stock, and we've added a new method. So we can instantiate my stock in the usual way. We inherit the initializer, the shares, the name, shares, and price attributes are set as normal, but we've got this extra method available. Here's inheritance to customize the behavior by replacing, overriding, or shadowing an existing method. So this one is popular when I teach it to this example, when I teach it to financial companies, showing them how to overinflate the values of their holdings. But one thing you might notice is the original implementation of the cost is that self.shares times self.price. Because we've overridden cost, when you instantiate my stock and you look up stock.cost, you'll get the overridden one, which has effectively replaced the original. But that means it's had to duplicate the original algorithm in order to modify it. So it'd be nice if there was a way of calling up, of using the parent implementation and then just modifying the result. And that's what super is for. Now, super is an interesting beast. In Python 2, we used to have to specify self and the class name, and no one, myself included, could ever remember which order it was. So it's one of the two interesting things that happens at bytecode compile time. It was changed in Python 3 to make it a bit more magic. The first interesting thing that happens at bytecode compile time is whether a variable is local or global or non-local is determined at bytecode compile time. So global and non-local are actually compile time directives. They're different bytecode generated. And the other thing is super is rewritten, and the instance and the class are passed in for you. And this means the use of super here, super.cost in this alternative version of cost, it calls up to the parent one, gets the result, and then modifies it. Now, it doesn't strictly call up. It calls the next class in the inheritance hierarchy. And when we're using single inheritance, that's always the parent. It's more tricky when we have multiple inheritance. But when you're calling up, when you're calling your parents, always use super. Don't hard code the class name. And it's particularly important if you're inheriting from a class, if you're overriding the initializer. It's a common, easy mistake to make, to forget to call super. And then when you instantiate your objects, you've got a partially initialized object. It's usually a mistake you discover very quickly because things start failing with attribute errors. But always initialize your parents. So in object-oriented theory, inheritance establishes and is a relationship. So an instance of my stock is a stock. An instance of stock or my stock is an object, because stock is a subclass of object. And in Python, the theory matches the practice, which is one of the reasons I like Python particularly. So the thing about inheritance is you inherit the whole API. And it may be that you want to create objects which have some of the stock behavior, but do you really want to expose the whole stock API? And we can use composition instead to solve that problem. Here we have a holding class that's defined. It doesn't inherit from stock. Using composition, composition establishes has a relationship, a holding has a stock, and then some of the API is explicitly exposed via delegation, but it doesn't expose the whole API of the stock class. So with composition, there's a bit of extra work to do with that manual delegation, but you have much more control over what API you're exposing. So that's an alternative mechanism. How are we doing for time? Still a bit of time left. Well done for all the listening. And I'm very happy with questions. I like questions. So thanks to those of you who contributed. Right, multiple inheritance. Classes can have multiple parents, and it can introduce a great deal of complexity. Don't do it. The only valid use case for multiple inheritance in Python is for mixin classes. And for that is very good. You do see multiple inheritance used for mixin classes. So I'll show you what a mixin class is and what problem they solve. And the thing about mixin classes is that it's a way of providing a limited and specific amount of extra behavior to classes. And it's that limited that is important that makes it practical. So this is the syntax. Instead of just in that tuple in the class definition line, instead of a single class, we can have multiple classes. And Python has a particular style of multiple inheritance called cooperative multiple inheritance. So if you do cooperative multiple inheritance and you design your code that way, working with the way that Python does multiple inheritance, it works straightforwardly and has some specific rules around it. If you try and do stuff against cooperative multiple inheritance, things get painful. And a big part of multiple inheritance is that we can arrange the parents to cooperate. So the order of the parents matters. Mixin classes always go at the front. They always go first. And what this affects is particularly attribute lookup. When we do object.method, the inheritance hierarchy defines how that method is found, where it comes from. Attribute lookup can jump from parent to parent, and the order matters. So let me show you something quite funky. We have a parent class. We have another class that inherits from parent. And in this class, you look at this definition, it's very clear where super.method goes to. We inherit from parent. So the super call goes to the parent, doesn't it? Then we have another class. that also inherits from parent. And similarly, this supercall goes up to parent. Now we have a third class that inherits from first and second. Does anyone know or wants to guess? Not a trick question, but a tricky question. When I call t.method, what will be printed out?
I'll go with first, second parent.
Is that Paul?
Yeah.
Yeah, very good, very good. So if we look at the code, I said the order is significant. So first, when we do t.method, this is the method that's found. It prints first, super.method is called, and that goes sideways to second. So we see second printed out, and then this supercall goes up to the parent. So if you're just looking at the code, it seems really clear what this is doing. It's going to go up to parent. And if we have an instance of first, that is indeed exactly what happens. Similarly with second. But as soon as we have multiple inheritance, the supercall goes sideways. And this is because the point of super is to go to the next class in the inheritance hierarchy, not always directly upwards. And this means if first is a mixin class, by putting it first, it has an opportunity to specialize the behavior of second. And it also solves the diamond inheritance problem. Prior to having, so in Python 2.1 and earlier versions, we had the old style class system. We didn't have super. And what you would have to do is you would have to hard code the parent calls. So you would do something like first.method self, second.method self to make sure that they were both called. And first would call parent, so you'd get first parent, then you'd get second parent, and parent would be called twice. And that's called the diamond inheritance problem. And there was a particular paper, the C5 linearization algorithm, which described a solution to the diamond inheritance problem, and that's what's implemented in Python. That's how super works. It builds something called the method resolution order, which we might get a chance to look at. We linearize this graph of parents into a linear order that we can call things that make sense, and there's a couple of rules, and I can explain those. Okay, so what are mixing classes? Why are they useful? What's the use case for them? Here we have two unrelated classes. Both are implementing the noise interface, the dog and the bike. And we want loud variants of both of them, but they're unrelated classes. So the implementation of noise for the loud dog is identical to the implementation for noise for the loud bike, but there's nowhere obvious for this common code to go. So let's have a look at this. We have class dog. Makes a noise. We have class bike that makes a noise. We can define this loud class it can make a supercall to noise. And look, loud itself has no parents other than object. So loud can't be used by itself. If I call loud.noise, I'm going to get an attribute error. Object has no attribute noise. What I can do is I can create a loud bike by mixing loud in to the bike class. Similarly, I can create a loud dog by mixing loud into the dog class. So loud exists to specialize classes that implement the noise interface. So now when I do loud bike, because I declared loud first, the noise that I get is going to be this one. It's going to call super. It's going to jump sideways to the next class, which is going to be bike. Call that and uppercase it. And the same with loud dog. So loud here is a mixin class. It allows us to mix in additional behavior to anything that implements a noise method returning a string. And they're very practical. Here's an example from the Flask web framework. The Flask login extension provides all the standard login, user verification, and registration functionality, and it requires the user model to have some particular methods available for it to work, and it provides those methods as a mixin that you can just mix in to your user model. You see mixins quite a lot in Python. They're very useful. So it's a valid use, the only valid use case of multiple inheritance in Python. It's kind of like aspect-oriented programming. You mix in a slice, an aspect of behavior.
So what is the advantage of using these mixins comparing to, you know, for example, abstract classes?
Compared to what, sorry?
To abstract classes and the ABC, you know.
So ABCs define the interface, but you don't typically use them to, and in fact, a lot of ABCs are provided as mixins. If you look at collections.abcs, sequence, mapping, mutable sequence, you can use them as mixin classes. They provide the abstract definition and and they provide some mixin methods as well. Have you seen the protocol classes in Python 3.8? They're like ABCs on steroids, typing.protocol.
No.
If we have time, I'll show you them. We probably won't have time, but they're very cool. They're like abstract base classes, but you don't even need to use inheritance. It's sort of more like structural typing from Go. They're great. But yeah, it's a little bit different from abstract base classes, which provide you with an abstract definition of the interface, but doesn't typically provide much concrete code. Okay, so now we get to the really interesting bit inside Python objects. So prior to object-oriented programming, we had procedures, functions, and data structures. And if you think of a dictionary, particularly a dictionary with string keys, it's a mapping. You can think of them as a mapping of names to objects, a namespace, and they're fundamental to Python. And Python is really a bunch of layers over the top of dictionaries. So the attributes on an object, there's a mapping of names to objects. The globals in a module, there's a mapping of names to objects. The members of a class, there's a mapping of names to objects, and they're all dictionaries, unless you use slots. Well, you don't use slots. So every object has an instance dictionary, which is available to us to look at. So let's create an empty class. Let's create an instance. Let's attach some attributes to it. Now let's look at the instance dictionary. That's the instance dictionary of the object. That's where the attributes look. And those fundamental operations on attributes, fetching attributes, setting attributes, deleting attributes, correspond to operations on the underlying dictionary. So fetching an attribute, set a new attribute, I've poked it into the instance dictionary, and now I can look it up, delete it out of the dictionary again. That attribute is gone. And similarly, there is a class dictionary. You get a bunch of stuff put in it by default by virtue of class creation, but there's the attribute I just created. And so every instance has its own instance dictionary, and this is how every instance is able to have separate data. The class members, those methods, or any class level attributes, are also stored in a dictionary. So when we do an attribute lookup, if I do t.foo, if I can find my mouse pointer, Python has to look in a couple of places. First of all, it checks, is it in the instance dictionary? And in this case, it isn't. So then every instance also has a dunder class attribute, a link back to its type. So if it's not found in the instance dictionary, Python can follow dunder class and can look in the class dictionary, and there it finds the attribute. So for a simple class, there's this sort of two-step lookup. First, check the instance dictionary. If it's not found, then go and look in the class. So there's a very simple diagram showing the relationship between different instances and their attributes and methods, attributes living on the instance and the methods on the class. Operations that modify an object update these underlying dictionaries. And it's because of these attribute lookup rules. First, look in the instance dictionary, then follow dunder class and look in the class dictionary. This is the mechanism by which class members are shared by all of the instances of the class. But because we can have multiple inheritance, the rule isn't quite that simple. There's a dunder bases attribute as well, which will tell us the base classes of a class. It says here, this link is used to extend the search for attribute lookups. It actually isn't. There's an MRO, method resolution order, and that's what's used. But conceptually, the dunder bases could be used. So if I look on thing, I'm going to find thing.dunderbases is only object. These are constructed at class creation time. So with single inheritance, here we have the instance little e, which is an instance of big E, which is an instance of big E, which is a subclass of D, which is a subclass of C, which is a subclass of A, which is a subclass of object. When we do e.attribute, attribute might be found in any of these places, but the order, the path that Python has to take to search for that is obvious, it's clear. It's first little e, then E, D, C, A, object. And that's the MRO, the method resolution order. Python walks the MRO to find attributes. And for single inheritance, it's clear. What should Python do here? What's the order Python should check and what makes sense? Inheritance is a graph here. Cooperative multiple inheritance, Python uses the C5 linearization algorithm to construct the MRO, and it follows two rules. The parents go in order, we've already mentioned, so we can specify the order. We can put the mixin class first, and the mixin class gets a chance to specialize the other classes. And the other rule is that children go before parents, because the point of subclassing is that children are able to specialize their parents, so children must come before their parents. And there's often multiple MROs that could meet these requirements, so there's a tiebreaker rule. It's a constrained merge sort of the parent MROs constructed at class creation time. So for that particular class hierarchy, this is the method resolution order. E, then C, then A, then D, then B. E, then C, then A. No, sorry, then D, then A, then B. Oh, no, it might be A, then D, then B. Yeah, E, C, A, D, B, I think it was. Yeah, So there are a few rules, and we've just got time to cover this, and then that will be it. If you're doing multiple inheritance, if you're designing for multiple inheritance, there's some rules you must follow so that cooperative multiple inheritance can work. Because super is going to call the method for all of the classes in the inheritance chain, they must all have compatible method signatures. So you can add new arguments using keyword arguments with default values, but you have to be careful not to pass them on in super. So compatible method signatures is rule 1. Rule 2, there must be somewhere that terminates the method chain. If the very base class calls super here, it's going to go to objects. That's going to have an attribute error. It's not going to work. So it's common to see common base class with a bunch of maybe even empty methods that only exist to terminate the method chains. And rule 3, use super everywhere. If you hard code any method calls, here we go straight to base, and then B and C are never called. And the point of inheriting from them is because we want to use their functionality. You've then got broken code that can't be fixed. D can't fix this problem. It has to be fixed in A. So always use super. And that brings us nearly to the end of our time. Operator overloading is an interesting topic, but the protocol methods correspond to operations. Here's a simple mapping part of the container protocol. There's lots more we could talk about: abstract-based classes, protocol classes. I'll very quickly show you protocol classes, new in Python 3.8. This is structural typing, a bit like Go, runtime checkling and protocol. I can define an interface and declare it as being runtime checkable. Inheritance from protocol. I define a noise method that takes no arguments. Now I can define, have I still got dog? Is instance dog noisy? Dog is an instance of noisy because it implements, not because it inherits, but because it implements the interface. Because the noisy interface is runtime checkable, a class is considered to implement it if it in fact implements it. And there's no extra work to do. So you can define your instances, define your interfaces, and then you have successfully implemented them if you successfully implement them. That's the only requirement. So they're like ABCs on steroids. Okay, any questions?
What does super return?
That's an interesting question. It returns a super object on which you can do attribute lookups. It has baked into it. So if you think, let's go to an inheritance hierarchy. Let's have a look at. So this at runtime is, at compile time is rewritten to actually be like this, self and loud. That's what it's rewritten to. So when super is called, it says, what is the next class of the MRO? So self will be an instance of, say, loud dog. So it can go, Python can say, what's the MRO of loud dog? And loud dog is loud dog object. And so where am I? Where is loud? I'm the loud class. Where is loud in the MRO? I'm at this position. That means the next class in the MRO for the actual object we're working with, it knows which is the next one. So it's just an object that's able to do lookups. It knows the type of the object that we're doing the lookup on. It knows its class and it finds itself in the MRO and returns the next one. That's how it works. It's not very complicated. Does that make sense, Christian?
Yes, so it returns an object.
A super
rather
object. Yeah, yeah.
Okay.
Super. The other way around, it's the type and then the instance. This is why we like the new version. Oh, fiddlesticks. Love dog it. Yeah, anyway. Any other questions? Okay, folks, thanks very much. Thanks for coming. You are all free people.
Thank you so much, Michael, for running that. It was really interesting.
Okay.
Thanks,
I may
very
well,
interesting.
in a few weeks, I might do one on iteration, closures, decorators, and generators.
Thanks very much.
Thanks
That was
very
really
much.
good.
Nice.
Thank you.
Thanks a lot, Michael.
Thank you. Bye-bye.
Bye.
Bye.
Thanks.
Bye-bye.